Okay, here we are in part C, which will be about prediction for simple linear regression. This is definitely the hardest part of linear modeling. It's super easy to make mistakes in your code. And actually, before we get started, I want to point out a mistake in my code. I thought something was wrong last time, but I wasn't sure what it was. But I had these two things reversed here. So what I had in the code in part B, or vignette B, was sx2 over sy2, but it should have been the other way around. It should be rise in y over run in x. The resulting plot, which you can see over on the right, isn't that much different than what I had last time, and the reason for that is the spread of the x's isn't really that different than the spread in the y's. So the results that we got last time are, for the most part, correct because of that coincidence. But I encourage you to download the updated file or make the change in your own code so you can use the correct coefficients going forward. Okay, so prediction. So suppose you had a new x location where you wanted to make a prediction. So where you want to know what the distribution of y is at that x given, so this is a conditional distribution, the x's that you have in the data and the y's that go with them. Okay, so I want to understand this whole distribution. You could predict by using the estimated coefficients, and you might call that y hat of x, but that wouldn't be the whole distribution of y values of that x. That would just be the fitted value or the predicted value. I'm using a generic x here. It could be any particular value. However, in the code, what I'm going to use is a whole range of values. So I'm going to make a prediction for a whole range of x's. And in fact, I'm going to call that xp. So xp is going to be a sequence from 10 to 20. So that spans the whole range of the data plus some on both sides. I'll write NP, and then I'll make a prediction at 100 locations. Okay, so I have this whole range of values, and then my fitted value for prediction is just going to be my estimated intercept plus the slope times those x's, and you could call that yp or y hat. I'm just going to call it yp, and then I'm going to remake this prediction from before. I'll just grab the plot here, right? So they're remaking the plot, and then I can use lines and put xp for the x's and yp for the y's and make it a thicker line. And so I've put that line on the plot using the pairs of points xp and yp, where the yp comes from the maximum likelihood values of the coefficients at those x's. So another way to plot a line, a predicted line. All right, so again, what I really want to know is what range of y values could I get for all of those x's, and this doesn't tell me that. However, you can't see my plot. I apologize. Now you should be able to see my plot. So this looks very similar to the one that we made earlier 2 panels back, except I didn't use the AB line command. I used the lines command with my prediction grid XP and predictions YP. All right, now I can go back to the whiteboard. Understanding uncertainty that is the whole distribution of predicted values in simple linear regression is like a big confidence interval calculation. Actually, we're going to have two different concepts. We're going to have confidence interval and prediction interval, and I'll try to make clear what the difference is between those two as we develop some of the code. First, I want to be a little more concrete about what I mean by a big confidence interval calculation. So remember, with confidence intervals, we do a for loop just like with a hypothesis test, but instead of using a value that comes from the null hypothesis, we use the estimated coefficients. So let me go back up and find one of these for loops and go borrow it, and then I'm going to replace the null hypothesis value with the MLE. And I don't need to save the estimated intercepts and slopes, but I do need to use them. So I can get the intercept with mean of the simulated y's minus b1s times mean of the x's. So now I've got a way to sample from the distribution of both of the coefficients at once. And then I can take those and make a prediction. So I got b0s plus b1s, and I can use my predictive grid. And those will be the lines that I get under the sampling distribution of the coefficients. So I could call that, I like to call that YY means in my code. So this is going to be a whole vector. Because XP is a vector, the line is represented as a vector, and one of those lines is what we see in the plot, which I might as well put up on the screen now. So this is the line that we get with the MLE coefficients. That's going to be a little different than the line that we get from the sample coefficients, but they should be in the same ballpark. So let me make some space for this. This is a matrix with n rows and np, the number of predictive locations, columns. So these are the basis of a confidence interval for the line. And why is that? Because if we use the slopes or the intercepts and built an interval from those, that would be a confidence interval for those parameters. And this is combining the two sets of parameters for a confidence interval on the line. What's called a prediction interval comes from the additional uncertainty that you get when you take the line itself and add on the extra error that you get from the Gaussian distribution that your epsilons have. Remember, it's line plus error. So I have to add this extra randomness to get the error. So I have NP predictive locations, so I need NP Gaussian random variables, each with the same standard deviation square root of sigma 2. And I need to make some space for that. So this is a simulation for confidence interval and prediction interval in an SLR. And hopefully this will run. Okay, we need to do a little more work to get the visuals. It's not as simple as a histogram. I want to show you these lines that I'm getting. In particular, I want to show you these ones because they don't have the extra randomness in them, which will be kind of ugly to look at. You're welcome to try to plot that on your own. I've got 100,000 of these lines because that's what capital N is. And that's a lot to look at. So I want to look at a reduced set of YY means lines. So I'm going to create a variable called cell for selection, and that's just going to be a sequence from 1 to n by 100. So I'm going to show you every 100th line out of the 100,000. And I can do that with the matplot command. Put the x's in, and I have to transpose this matrix of YY means in order to get it to work with the matplot command. I want them all to be interpreted as lines. I want them all to be gray, and I want them all to be just ordinary lines. Hopefully that will plot them. There we go. So those are all of the lines that I get from all of the intercepts and slopes and this grid of prediction locations. And I can put the data back on so you can see how the data kind of inform the lines. And like I said, I made the prediction grid include more to the left and more to the right than I had in my data, basically so you could see the uncertainty or the variability in those lines fan out as you get farther from the middle of the data. Okay, so that's visualizing the lines. Now, how to get a confidence interval for those lines. And as usual, we extract quantiles. So I need to use the quantile command, but I need to use it for every column of this matrix. So the way that we do that is to use apply. Apply can take an object like YY means, and then apply over the second dimension, which is the column. And then I apply the quantile function with prob equals 0.025. So for 2.5% quantile, I could call that low confidence interval. And then I can put that on the plot. Whoops, I didn't run it. And it's not line CI, it's low.ci. All those mistakes, but I think I still got the right result in the end. And then I can cut and paste this for the upper one, high CI, and do 0.975, and then do high CI, and then get the other one. So that's my confidence interval for the predictions from the confidence interval for the estimated coefficients. A prediction interval uses YYS and has the extra epsilon from the Gaussian. Okay, so I can copy the same code, but it's now going to be a prediction interval using YYS, prediction interval, YYS, prediction interval, prediction interval. And hopefully I got all of them. Oh, but I don't want to make it red. Let's make it whatever color 3 is, which is green, and then color 3. Okay, so there is my prediction interval, which has extra uncertainty because the lines are observed when we collect data with some additional noise. So the code on that is a little bit difficult, but it's really just a confidence interval calculation, or this extra line gets us the prediction interval. So I should say for PI here to be complete. And then we need a way to visualize those lines, and in particular to visualize the intervals summarizing our uncertainty. So now we can make a prediction, and I can put the lines of that prediction back on. We had that here, so why don't we put that on there as well, actual prediction, and then give an interval. So if I want to predict at 19, I go here at 19, there's my prediction, but the value of the line could be anywhere between these two red points, and the value of the actual point around the line could be between these two green points. All right, so maybe you thought that was difficult, and if you did, you're going to think this next part's even more difficult, and you're going to hopefully like the simulation better. So how do you do this with math? Okay, so if you didn't have a computer and couldn't do the simulation, what would you do? Okay, we already defined, but I'll write again. So denote y hat of x as what you predict with maximum likelihood coefficients. Okay, with MLEs for the coefficients. And then I want to call y twiddle of x this same thing with the extra error, where the error is IID Gaussian with a mean of 0 and a variance of sigma squared. So I'm just setting some stuff up here because I want to take you through some calculations sort of from simple to more difficult. Okay, so starting a little bit easier. Consider what is the expected value of the distribution, the full distribution of all the y's, y twiddle. I can then distribute that expectation through the linear equation using linearity of expectations. I'll get but this is 0 because of that 0 in the Gaussian distribution. And we already know that we have an unbiased estimate of the intercept and slope. So we can see that our prediction y twiddle is unbiased because that's what you would get with the expected value of y of x. And similarly, you could go through the same calculation for the expected value of y hat of x, because that's basically the same after you do the expectation of epsilon. That's going to be equal to the full uncertainty. So all of these things are unbiased. But that was really just a little bit of a warm-up. We know that the average of our predictions is the truth, which is a really good property to have. What's more important for the prediction picture is the variance. So let's look at the variance of the prediction, the hat one. Again, linearity of variances. But I get an x squared because x is a coefficient out front of a variance. And then I'm going to get a plus 2x cove beta naught hat beta 1 hat. So I have two random variables, beta naught hat and beta 1 hat. So when I do linearity of variances, I'm going to get a covariance term. I already know some of these things. This is sigma b0 squared, and this is sigma b1 squared from Vignette B in chapter 7, so from the previous video. This I'm just going to tell you what it is. It's minus sigma squared x bar over n minus 1 sx squared. I'm not going to derive that for you, and I don't do it in the book for this chapter either, but I do it in chapter 13 in a slightly bigger case. Chapter 13 is on multiple linear regression. So I'm just asking you to wait a little bit. It's actually easier when you build a little bit more scaffolding in chapter 13. So just take my word for that now. When you combine all of these things together, you get a formula where you've got a sigma squared out front, and then you have 1 over n plus x minus x bar squared over n minus 1 sx squared. And that's algebra that you can totally do. That's not hard. And this has a special name in a lot of software. It's called S-fit squared. So the yx is kind of the fitted value for a new input x, and its variance is S-fit squared. And you can see that you can reduce that variance by increasing n, which is in the denominator in both parts of that sum, or you can make a prediction closer to the middle of the data because of that squared term at the top. Or you can decrease the variance by increasing the spread, sx squared, in the denominator, if you have the opportunity to design an experiment. So how do we use this in practice? We replace the unknown sigma squared with the estimate, the bias corrected estimate, and use a student t distribution with n minus 2 degrees of freedom. So we know we can use the prediction as its mean. That's what we figured out up here at the top, and we know what variance to use, and that'll give us our confidence interval. And let me show you what I mean by that. So going back over to R, now the math way. So I'm going to define S-fit squared, or sometimes I write S2 fit, sometimes I write S-fit 2. I'm not always consistent with that. So I've got my estimated variance, and I've got 1 over n plus xp minus x bar squared divided by n minus 1 times sx squared. Okay, and then I'm going to take the square root of that to make my confidence interval. So S-fit is square root of S-fit 2. And then I'm going to do the low part of the confidence interval. So that's going to be what I predict, which is yp, plus a quantile of a t distribution with n minus 2 degrees of freedom and 2.5%. And then I'll multiply by the standard deviation. The t distribution in R doesn't allow you to specify a standard deviation, but you can just take the values that you get and multiply by the standard deviation. You can also do that with a Gaussian distribution. So, what did I do wrong? What is n? 10. I said it should be n minus 2. What did I mess up? S-fit 2. Those are all reasonable. Oh, I'm just getting these arguments backwards. I'm not even looking at my notes. So this is n minus 2. Whew. Okay, told you it's easy to make mistakes. Okay, so lines, XP low. Oh, I didn't mean to write over the low CI from before. Let's do low CIT. We can, just in case we need it, we can put this guy back. And then we'll call this low CIT. Let's do a new color, 4, and let's make it dashed. And let's see how it shows up. Yeah, so you see that? it's barely, it's covering, see how this guy's now dashed? It's exactly covering the lower part of the confidence interval that we calculated by simulation, but it's using the math instead. And then we should be able to get the upper part of that confidence interval with 975. Hopefully that'll be good. Look, perfect. So that gets the higher end of it. And then again, more cutting and pasting. Oh, I got to tell you the next part. Okay, so let's go back over to the whiteboard. The last step here is to do the full uncertainty. So let's grab that. Now, with full uncertainty, including this extra epsilon. So the variance of y twiddle, oops, that's a little sloppy, sorry, is going to be the variance of our fitted value plus the variance of epsilon. Okay, and this is just sigma fit squared, and this is sigma squared. And you could call this S pred, or sigma pred squared, and it's a function of x. And this guy is also a function of x. And so you can use S pred of x squared, which combines those two formulas. So I'm going to get an S squared out front, 1 plus 1 over n plus x minus x bar squared over n minus 1 sx squared. So this part of it is the S fit squared part, which is the same as before, and we're getting an extra factor of sigma squared, or S squared out front. Actually, that should be pointing at the 1 there. So if you look at these two formulas, they're both on the screen here. The fit one, I can make the fit uncertainty 0 by taking n to infinity, by getting more and more data. But even if I get a lot of data here at the S pred part, I've always got this extra 1 here. I've always got some extra uncertainty that comes from the variance of epsilon, which is my measurement variability when I collect the data. Okay, let's code this up. This is actually pretty easy. So this was for confidence interval calculation, and then prediction interval calculation. I've got to calculate S pred, which is the square root of S fit squared plus S squared. That's pretty straightforward. And then I should be able to grab this code and change all the C's to P's and make sure I use S pred and then P and P S pred. Better change the colors too. 5, 5. Hopefully I got everything. We will find out. All right, that's a little hard to see because I think let's make this LWD equals 2. LWD equals 2. And let's change the color to 6. I think we got the lines correct. We just can't see them. There we go. All right, so putting it right on top of the simulated one that we had before, but this time calculated with math. So I know that's a lot, but if you break it down into things that you understand, it's not too bad. Really, the only thing that I wasn't able to develop from scratch for you, going back to the whiteboard here, is this, which is in chapter 13. That was the only thing that I kind of waved my hands at. Okay,